This assessment asks us to sketch the signals we would expect to see for HA, HB, and HC in the molecule given. Now, the interesting part of this question is that there's a different coupling constant between each set of hydrogens. The coupling constant between A and B is 2 Hertz, the coupling constant between A and C is 7 Hertz, and the coupling constant between B and C is 5 Hertz. Well, let's start by doing this with HA. Now, HA, let's just imagine, we can do a splitting tree. We're going to imagine a signal that shows up at that position. If HA had 0 neighbors, it would be a singlet. It actually is going to have HC as a neighbor, and the AC coupling constant is going to be about 7 Hertz. With HC as a neighbor, HC is going to make HA into a doublet where the coupling constant is about 7 Hertz. Now, if we had a ruler, it would be easier to do this. I'm going to put a dotted line to say that this difference is 7 Hertz. And as a result of what's happening, this is because it's a neighbor to HC. So HC makes HA a doublet. Now, HB can also be thought of as HA's one neighbor, and HB being one neighbor would make HA also into a doublet, this time with a coupling constant of 2 Hertz, so a smaller value. And so what we can do is we can take both of these doublet lines that are now HA because of HC and split those into a doublet as well, where we are intentionally making this coupling constant smaller. Again, if we had a ruler, we could check, but we're saying that this difference here is 2 Hertz in both cases. And this is a result of HB. HC makes HA a doublet with 7 Hertz. HB makes HA a doublet, but with 2 Hertz. The net effect of this is that we end up with a spectrum that looks like a doublet of doublets. HA would appear as a doublet of doublets. Try HB and HC on your own following that same process.